We continue with this part of fragmentation pattern with the different organic compounds. We start with the first group, which is alkene. Alkene always fragmentize into simple alkyl group. If we tend to loss of methyl, M plus minus 15, loss of ethyl, M plus minus 29, loss of propyl, M plus minus 43, loss of butyl, M plus minus 57. Branch alkene tend to form the most stable carbocation. We see in this mass spectrum how we can determine the fragmentation peak and how it had been lost for this hexane organic compound. So we can see here the peak, all these peak have not every single peak we need to analyze. We have to base on the prediction of the loss of the alkyl group. So here we can see the molecular mass of this compound is 86, and this peak, how to reach this peak, is 71 peak. So means 86 minus 71, it becomes 15 in the middle. Always in the middle, when we deducted here, it becomes a radical. Means this molecule has been lost of the methyl group, which is CH3 mass 15. So 86 minus 15 becomes 71. So we know this part is the first loss. So this is the first fragmentation. And next loss will be 86 minus what become all this peak. We can see, let's say we take the more base peak, which is the stable peak. This peak is all around the 57. 86 minus 57, it becomes 29. So this peak is one loss. 29 we know just now is a loss of ethyl group. So ethyl group, where is the ethyl group? So this is the loss of ethyl group here. And next loss will be next peak. So 86 minus what become? We have to predict which one peak. We have to make synchronize with our molecule. So 86 minus 43 become 43. So 43 is loss of propyl group. And the last one is the loss of 57. 57 means the loss of butyl group. And this is the break here. And if break here, this one become radical, this one become a cation. You have to determine which one will be appear in the mass spectrum is only the cation. In between, when you deducted, is always radical. You understand? I mean in between. In between means here is 15, this one is radical, this one is radical. This one is 29, the radical is 29. The leftover appear in the mass spectrum is a cation. That's how the hexane loss. So same goes for, again for the same example. So this is the full fragmentation pattern that we can write down. And the missing things here in this fragmentation patterns is the loss of what? You have to written down the loss in the middle of the arrow, or you can plus with the radical here. CH2, let's say this one, plus with CH3 radical. And this one plus with the CH3, CH2 radical. So, or you can write down in the middle of the arrow. CH3 radical, CH2, CH3 radical, all these radical must be written down. This is called as a fragmentation pattern. You see the initial molecule is be written down as a radical cation, followed by a different fragment. Different fragment, you have to show the things that appear in the mass spectrum will be always written down the MZ value below the cation. The radical, we no need to write down the mass of the radical, just show in the fragmentation pattern. Next, the example is this structure of a high alkene group, and sometimes it's not lost only the follow the alkyl like methyl, like propyl, like butyl, but it's also can loss of 14, which is possible to lose 14. Just now the first consideration we should take. Next example. This example, we have to deduct how we can predict the loss of what? 142 deduct by 113 means loss of 29, I think. Or loss of what? You have to deduct and you get the gap here and you predict based on this structure where's the loss is. Next, the mass spectrum of 2-methyl pentane. So this shows you the mass fragmentation pattern, and how we can write down here. This is a complete mass fragmentation pattern when the radical cation is written, and this is the loss. We have to predict the loss. Like say I've lost here, the loss CH3. The loss of CH3, this part will become cation. So where is shown here in the mass fragmentation pattern? Here. And this part will appear, so the MZ71 appears. So have it? Yes, correct. So this is the first fragmentation. And next, I can predict here the loss of this part. The loss of this part, so this is the loss of that part, and this one is remain as cation. So the MZ is 43 here, the most stable one. Here, the most stable. And if the loss of branch is quite rare in the alkene group, that's why I lost here. So when I lost here also can. So this part will remain as a cation, and this part will be lost as a radical. This is a full fragmentation pattern with the complete written down with the radical and the MZ. You see, the radical are not written down the MZ value because it's radical, not appear in the mass spectrum. Only this peak appear. So this is how you can write down the fragmentation pattern. This is for alkene. And for this question, how we can distinguish two alkene between C7H16? This structure with the molecular formula same but chemical structure different. So how we can determine this is have a loss of here and here. So this part we cannot see the loss of 29, the MZ29. Okay, we can see the loss of 43 and the loss of 57. These three peaks will appear, and this one 15 also same. And we can see obviously the loss of M29, which is cannot be found in this structure. That's why how we can differentiate. And this part is 71 also we cannot see in this mass spectrum. So that's how we can predict how to differentiate between these two molecules, because the fragmentation peak and fragmentation pattern is different for both. So answer this question, you have to show me the fragmentation patterns in details with the presence of which one as a radical cation, which one as a radical or cation. Okay, next we go for the next example is chloropropane. Same, is like a alkene group which is lost methyl group. It will lost is this part, or we can loss of chlorine atom. Same goes to this part. The loss of branch is quite rare, so most probably it will break here in the middle, and loss of CH3 only. That's the possible things. And this is how the benzene ring, the alkene with alkyl group with the benzene ring. So it not tend to loss here, it tend to break in here, or in the CH3, loss of 29 or loss of 15. Okay, now go for the fragmentation pattern of alkene group. Alkene group is typically from resonance stabilized allylic carbocation. If you can see, this is double bond, and this is the CH2 and this CH2. This is allylic position, which is it tend to break here. It not tend to break here because this is a stable allylic position. So most of alkene will break in the second CH2, carbon. So this allylic position very stable and always appear in the alkene group. So this here also where it can be break, so CH2, and then here it can be break. So this one is form a stable allylic. So you can see this CH2 and this CH2, and in this position it will break. So it not break here, it break in the second CH2. So the MZ, the most stable one is MZ41, will be appear as the base peak. You can see. So retro-alteration only happen for cyclohexene, whereas this pi bond will be transferred. We form a 3 different pi bond, and then this part will be break. So we can see when the electron transfer here, this electron will be transferred here, and this bond will be transferred here. Now this between here will be break, and this will form this dialkene stable compound with a neutral compound. This is only for cyclohexene. So can I show you just now? The electron have been, the pi electron have been transferred to form 3 pi bond, and then it will break here to form a radical cation and also the neutral molecule, only for cyclohexene. Okay. So again, it shows us the position of the stable one. Here we cut off, so this part will become a base peak, which is the mass value of this one becomes 68, and this is the benzene ring, the cyclohexane itself become a base peak. So that's the example is alkyne. Alkyne also same as alkene, which is the loss of propyl cation is the most stable, and you can see here this part how the alkene and alkyne shows the same thing, which is propyl, and this one is allylic position, all in the second CH2 of the bond. It will break here, same for both group. You can see it tend to form, this one is stable cation, this one also the most stable cation. So we can see here, so this CH2 and the second CH2 only will be break. It cannot break here, it will be break. It will break here, and then it will not break here. So aromatic, the fragmentation of aromatic is always will be rearranged when benzylic carbocation form. It will be rearranged to form a tropylium ion. So the tropylium peak will be appear as the base peak with 91 MZ value. You can see how the tropylium have been formed. So when the electron will break at the CH2, it's not cannot break here, it can be break here. So when it break here, it become cation benzylic, and this rearrangement of the electron will form in the cloud of electron of tropylium. It can be presented like this. This one, when it transfer inside the ring, it become here, and again retransfer. This means resonance of this structure. It will be represent as tropylium ion with the MZ value 91. So it shows you here how the electron have been cloud around the benzene ring. So here, this is the tropylium, the most base peak, which is the most stable tropylium ion for aromatic. And this is the benzene ring, and this benzene ring to form C4 for the alkene group, and this is the MZ value 51. You can see the mechanism how this bond, this cation have been formed. So the electron here now break here. So this part will become cation, this part become a neutral molecule. This is the fragmentation patterns for the aromatic. Okay. This one is a nitro group, nitro oxide will be released here and remain the benzene cation with the base peak 77. and based on this benzene cation also, we can break into this C4 ring and this neutral molecule. Next group will be the alcohol. So alcohol, it tends to loss of what? Because it have a functional group of hydroxyl, so it tend to lose hydroxyl, or it can tend to loss of the water. Commonly, loss of alkyl group always form the first degree alcohol with the prominent peak with the MZ value 31 correspond to the CH2O plus H. So this is carbonyl cation. So this is the most stable. This means this is the base peak. So it tend, rather than loss of OH, it tend to loss here. This part will become the most stable cation in the alcohol group. We see the loss of water and minus 18, and the loss here, this one become the most stable cation in the first degree alcohol. So this is the example for pentane 3-ol. Pentane 3-ol also same when it lost CH2. Let's say both sides same. So in this case, it lost the most stable one. It lost CH2, CH3. Either side also same. When it have formed this part, so this part will become the most stable cation with the base peak. This one is the loss of, I think, MZ 29. So next example. So this peak is 88. The molecular weight is 88, and then this peak is this cation, and peak 31 is this part. Oh, the half of this one have been lost. Next, for phenol, same. The fragment is due to the loss of carbon monoxide. It will loss of carbon monoxide, and less M plus minus 29 is less intense than M plus minus 28. Okay, next group is amine. Amine group same. It goes for the first CH2, like group of alkene, alkyne, alcohol. They are tend to form this part as a iminion ion, which is the most stable cation. So this is called as a alpha cleavage. Where this is alpha position, this is a beta position. We can see the loss of this one all after the CH2 will be break. Same goes for all different group I showed you just now. Group ether, same. If we go for the alpha cleavage, tend to form alpha cleavage after the CH2, and this is for ozonium ion, which is the most stable, and rather than that also can be break here. So this is the example of mechanism that we can write down, the mechanism of fragmentation. So this is what cleavage. So actually this one is a homolytic with the transfer of both electron. So and then also why they call it alpha cleavage, because this involve the transfer of electron, free transfer of electron. Or only mechanism, it is alpha cleavage. This because this one have been break, right? Oh, this one have been break, so also known as alpha cleavage. The mechanism shown should be 3 processes. If like this, we show this is homolytic, not heterolytic. Although this is also alpha cleavage, it can be shown in heterolytic cleavage. So this is the next mechanism. We have to predict how MZ31 have been formed by the transfer of electron. We can show whether homolytic or heterolytic. There are no false and wrong when you show me whether it is homolytic or heterolytic, because both are acceptable. So this is the diethyl ether. When you see this, will tend to cleave the CH3 with the loss and form this part, and also can be cleaved here, and this part will become a cation, and OCH2, and this part will further fragmentize, and this will be lost and form this cation. Okay, so as conclusion for all different group from alkane to ether, you can see the same trend, whereas they are in the position of alpha cleavage. Means that after the functional group, the first carbon alpha and beta will cleave. This one is the functional group, this is alpha beta, this is the functional group, this is alpha beta. Same goes to this one. So this is the functional group, this one beta between alpha and beta, so it cleave here. And this functional group, this is alpha, this is beta, so it cleave here. And this one is a functional group, this is alpha and beta. All this one tend to have a alpha cleavage at the position of CH2 after the functional group. Okay, now we go for the group of carbonyl group, which is the group of aldehyde, ketone, and ester. So as we can see, the position of alpha and beta is here. So after the functional group, it becomes alpha and beta here. It tends also to cleave at the alpha and beta. So here it can be cleaved both sides. RCHO means R, C, double bond O, H. So this one is position alpha, this one is position beta. You can cleave here or cleave on the right side or left side. So here is the example. Can be after C double bond O on the left side or right side, it can be cleaved. So I show you here, this is how aldehyde can be cleaved. So why it cleave here? Because the alpha and beta position is here. Because the functional group is O. So this is alpha, beta, so same as a alpha cleavage. So it can be both sides. So this is the example for the aldehyde group. It can be cleaved here, cleave in this part, and further cleave for this part. And all the before you cleave, you have to refer the fragmentation peak in the mass spectrum where it should be cleaved. Next, the ketone, same as I said just now, in this part and this part. So left over, if this part is left over here, and if this part is left over here. So this is for ketone, cleave here and cleave here, so remain a different part of the cation. So both appear in the mass spectrum. This part also appear, and this part when you cleave also appear. So ester group the same. If we cleave on the right side or left side, and we left the cation for different side. Here example, if you cleave here, so now if this part will be appear, if you cleave here, this part will appear in the mass spectrum. When you cleave here, the benzene ring tend to form this C4 ring, and with the MZ51, or you shown in the aromatic. And for the carbonyl compound with the position of gamma hydrogen, you have to know that they will undergo McLafferty rearrangement. This is very important in the carbonyl compounds. So what happened for this alpha? So position of alpha, beta, and gamma here. So this gamma hydrogen tend to react with the oxygen to form the hydroxyl bond, and this one will be break. This one when they combine, it become a spherical hindrance 6-membered transition state. Okay, when the hydrogen attracted to this oxygen, now it become one bond. When it form this spherical, then it will be rearrangement and eliminate the neutral molecule, led to the elimination of neutral molecule. So it will be arranged. The electron here will transfer here, and this bond will be break. So this one will be remain as a neutral molecule. You understand? After spherical hindrance 6-member, and this electron will further transfer here. Now this one become a double bond. This one will be break. So now it remains like this. This one become cation, this one become neutral molecule. This is when the carbonyl compound has alpha hydrogen only. So they will undergoes the McLafferty rearrangement ion. Next fragmentation pattern, rather than carbonyl group, is for natural compounds. For natural compounds, same as we mentioned. The first, if nitro, it tend to lose nitro dioxide, nitro monoxide. So it's a common loss, and it form if the benzylic ion, it will form this carbon 4 cation. And for bromine also, it tend to lose bromine, and the halogen, if have any halogen, it tend to lose the halogen first, followed by all the alkyl group in the organic compound. Okay, this is chloropropane, how we can show the mechanism. This is electrolytic, how we can show you. Also, it can be shown as a homolytic. Both can be shown. It depends. There's no false or wrong, but the mechanism should be logic. So that's all for different organic compounds, the fragmentation pattern, how they can be break. So how we can detect the mass spectrum. In our instrument, we have the GC mass. We combine with the GC, so we can analyze the mixture of the compounds by the GCMS. Okay, that's all for the fragmentation pattern of different organic compounds, and we will continue with the next session. Thank you.